Hello, class. Yesterday, we left off taking notes about the two types of energy waves. And I told you that by the end of this week, you should be able to compare these two types of waves. In fact, that's what you will be working on a little bit for the next assignment today. So anyway, one of the things that we discussed was propagation yesterday. And if you remember, propagate means to spread. And so energy waves, both of these energy waves do spread energy, but they spread them differently. Mechanical waves can spread energy both longitudinally and transversely, and electromagnetic waves only do it in a transverse manner. So today we're going to tackle what those two words really mean so that you can add that to your comparison of these two types of waves. All right, so transverse propagation. Description or definition is the first box that you have to fill in on your notes. Notice that that is at the top of the screen. Particles of the medium are vibrated from their rest position in a perpendicular direction to the direction that the energy wave is moving. Okay, so that's a lot of words. Let's kind of dive in and see what that really means. Down at the bottom of your screen, there is a diagram. So we're going to break this down with the diagram. You have an arrow here showing you that the energy wave is moving from left to right in this diagram. So that means that there was some kind of force here that occurred that created that initial disturbance of matter. And when the energy wave is coming through, okay, what particles used to be on this rest line now are getting vibrated up and down as the wave is moving from left to right, okay? And so this highest point right here is where the particles can move upward when the wave comes through, and this lowest point is showing you where particles may move as they move downwards. So again, they're kind of just getting vibrated up and down. And as the energy wave keeps coming through, these particles over here that got bumped in initially will kind of gradually slow down and come back to rest. Let's look at this website real quick. And I'm going to scroll down. You can come back to this again when you're studying if you want. But here is a transverse wave. I don't love this, but I do like a couple of things about it. First of all, again, we're going to think about it as the energy is moving from left to right on this virtual wave here. And the black dots are going to be the particles of the medium. And as the energy is moving through this medium, it is causing the particles to move up and down from their original position. And what you'll notice is if you stare at a single particle for a second, you'll notice that it's not moving with the energy wave that's moving through it. It's just getting vibrated up and down in its position, okay? When the energy starts to die out, again, those particles will go back to its so-called rest position. All right, back to your notes. I do want to point out also, in case you don't know what perpendicular is, it does mean a 90-degree angle. And so we are going to be doing an activity next week where you will be drawing and making some waves. And so we'll need to know what perpendicular means in a couple different scenarios. All right. Next thing is we're going to talk about longitudinal propagation. The definition or description is at the top of your screen. Particles of the medium are vibrated from their rest position in a parallel direction to the direction that the energy wave is traveling. So if you look down at the diagram below, you'll see that this wave looks a little different. It may not look like what you would draw as a wave. Here's how it works. Over here we have what's called a tuning fork. So this tuning fork is hit with something to make a sound. And what happens is the edge of this tuning fork will then bump air particles. And those particles are going to bump back and forth, back and forth, back and forth, knocking into other particles and spreading that energy wave from left to right. And this is longitudinal because the bumping back and forth is parallel to the actual direction that the energy wave is moving right here. That shows you the direction of the energy wave. Okay. Looking at the website, the longitudinal simulation is a little bit better, I think, than the transverse simulation on this website. I like here, this gray bar over here on the left side of the top diagram is simulating a force. So there's some kind of force, pushing force, that is causing this matter right next to that gray bar to hit other matter. Notice that the matter that's right next to the gray bar is hitting the matter and then coming right back to its position. Now, if the energy wave was to keep moving and there was no additional force over and over again, the particles right next to the bar would eventually stop moving or go back to their so-called rest position. It's kind of cool if you look at the red dots, there's a couple in the middle of the energy wave being shown. You can really tell they're just bouncing back and forth and they're still going parallel. There's no perpendicular movement of them, it's just parallel movement. All right, so we're going to head back to our notes. I know your notes ask you to draw diagrams. So what I would suggest is for a transverse wave, you want to start with drawing a rest line, which is this gray line right here. And you can go ahead and label it rest if you want. And then you want to make sure that you include in your diagram a direction of travel. So you're talking about the energy wave travel. And lastly, you are going to draw this wave pattern going up and down across the line. What might be important is that you do show an arrow going from the rest line up to the top part of the wave, and from the rest line going down to the bottom part of the wave, showing that there is movement of the particles going both up and down, and that is the farthest that they'll move based on that energy wave. Now for longitudinal diagram, this one's a little bit more difficult to draw. So we're not going to worry about drawing a rest line on this one. I would just kind of draw what that top diagram shows. It's showing spread out lines, grouped together lines, and then spread out lines. And what I would almost do is draw some arrows that point both left and right so that you can kind of see this movement going back and forth as particles are moving in this direction. And don't forget to add a single arrow pointing from left to right, showing the direction of the actual energy wave. All right, so that may be a little confusing. We'll touch back on this tomorrow. But that is the gist of longitudinal versus transverse propagation. To review, we learned about two types of energy waves. So at the bottom of your notes, you're going to notice you have the same diagram. Which side would you put mechanical, and which side would you put electromagnetic waves, and why? I would like you to try to fill this in. Obviously, the top layer right here are going to be your two types of energy waves, and down here are the ways that the energy waves can propagate. And we'll just kind of touch back on this tomorrow to make sure that you have it filled in correctly using the knowledge that you've been given through yesterday's notes and today. All right, parts of a transverse wave. So rest, crest, and trough are the three things that you need to know. We've somewhat touched on these already, so I just want to wrap this up. Rest, it is the position where the particles are when no energy wave is disturbing them. Make sure you fill in the blank of the information that's missing for rest. And then also there's a diagram below the definitions for the parts of a transverse wave. And you need to make sure that you label that rest line. This is something that I'll expect to see in your diagrams when we're talking about transverse propagation. Second definition is crest. It is the highest point the particles are vibrated as the energy wave moves through the medium. So again, you see that the diagram is pointing to 3 areas where it's showing the highest point particles can be vibrated for this particular energy wave moving through the medium. And then lastly, you have trough. And I have a feeling that this might be cut off, so I'm going to read this. It says the lowest point that particles are vibrated as the energy wave moves through the medium. And so this pointing to 3 different areas where that would be the lowest point that particles can move as the energy wave moves through. All right, so your definitions for parts of a transverse wave should be filled in, as well as the diagram beneath that showing what those are on a wave. Next on your notes is the parts of a longitudinal wave. Again, we're not going to have a rest, so we're just going to have the areas of rarefaction and compression. So your diagram is similar to the one on the screen. So circle the area where particles have been separated the farthest. That is where they've kind of bumped back apart from each other, and that's called rarefaction. And then circle an area where the particles are closer together, and that's where they're kind of being pushed and shoved together. That's called an area of compression. Those will be important in the next set of notes, so all these parts, because what we're going to be doing is talking about characteristics of waves, in which you have to do some measurements and calculations of energy waves in order to compare specific energy waves.